Dear student, welcome to my channel. Topic of this video is Extended Euclidean algorithm. Now let us start. Extended Euclidean algorithm builds upon the Euclidean algorithm to find out not only the GCD but also coefficient x and y such that ax plus by is equal to GCD of a comma b, where a and b are variables and x and y are the coefficient. This coefficient can be particularly useful in cryptographic algorithm like RSA. Steps for extended Euclidean algorithm. Apply the Euclidean algorithm to find out the GCD of a and b. Backtrack to express the GCD as linear combination of a and b. This algorithm involves maintaining additional variables to keep track of the coefficient during the back substitution process. Now we will see the first example. GCD of 16128. So to apply the extended Euclidean algorithm, you should know how to calculate the GCD. In my previous video, I have published the video on Euclidean GCD. Now see this 161. 1 minute. This 161 large number will come here. 28 into 5. So here we will keep one rule. Here both coefficient and variable both are in number. So whatever the quotient which will act as a coefficient, we will present in a bracket form. Therefore 161 is equal to 28 into 5 plus 21. Then next 28 come here and 21 come here. 28 is equal to 21 into 1 plus 7. Next 21 will come here and 7 will come here. Therefore 21 is equal to 7 into 3 plus 0. Now we have to calculate the coefficient. So here we are not taking the final equation in which one of the value is 0. So we skip this equation. Now when we are calculating the GCD, at the same time we are parallelly writing this line. So 161 minus 28 5 is equal to 21 and 28 minus 21 is equal to 7. So we just make the equation in which we keep here minus and plus equal to, here minus and equal to. So we are just rearrange this equation. Now we have to backtrack. So we start with this equation. Now here all 28, 21, 7, they are all variables, and whatever in bracket they are coefficient, and we always substitute for the variables, not for the coefficient. Now here 28 minus 21 is equal to 7. Now available variable is 21. So instead of 21 we will replace this 161 minus 28 5. 28 minus, instead of 21 this whole equation will be replaced, that is 161 minus 28 5. Outside coefficient is 1. Now you know when we multiply x by 1 it does not make any change. So when multiplied by coefficient 1 it does not make the change equation, so we can ignore this also, is equal to 7. So 28 minus 161 minus plus 28 5 is equal to 7. Total 28 6 minus 161 is equal to 7. So here a and b are variables. So here we are calculating the GCD of 161 28. So they are nothing but the a and b, and we calculate the coefficient, that is x and y. So here x is our, with respect to 161 it is minus 1. So here x is minus 1, and with respect to 28 the number is 6. So our y is 6. So in this way we apply the extended Euclidean algorithm to calculate the values of coefficient. Now here the same problem we can solve in tabular fashion also, but when we are solving the problem manually, at that time this method is fast, and when we are implementing in computer this method is efficient. Now I will explain the tabular approach also. So R1 R2, in R1 always our large number is there, 161 21. We will calculate the quotient is 5, remainder is 21. Now here we, in the first step we will initialize S1 S2 T1 T2 to the values 1 0 0 1 respectively. So here S1 S2 and T1 T2 they are initialized to 1 0 0 1 respectively. After that, once we calculate the quotient, we will update the value of S and T. So S and T gets updated. This is the updated value of S and updated value of T. So in the next iteration, like Euclidean GCD, we copy 28 here, 21 here. Again we will calculate quotient. again we will calculate the remainder. Now we are doing the shifting, that we will move s2 to the s1, s to the s2, then we will calculate the new value for s, then t2 to t1 and t to t2, and we will calculate the updated value of for t. So this will be continue until our one of the number becomes 0, because when one of the number is 0, then at that time GCD is another number. So at that time we stop here and we will see the updated values of coefficient come in the variable s1 and t1. So s1 and t1 are the final answer. So with respect to s1, that with respect to s1, the value with the largest number, that is -1, will come, and with respect to t1, the value with respect to smaller variable, that is 6, will come. So in this way we can solve the problem by tabular fashion also. But when we are solving manually, at that time it is very tedious to update the values and shift the values. Instead of that, this method is very fast. Now we will see the another example. 2611. So large number will come here. 26 is equal to 11 into 2 plus 4. At the same time we will write down the equation. 26 minus 11 2 is equal to 4. Next, 11 is equal to 4 into 2 plus 3. Then 11 minus 4 of 2 equal to 3. Then 4 is equal to, this shift here, 3 into 1 plus 1. Then next 3 and 1. 1 into 3 is 3 plus 0. So we are not taking this equation. So first three equation we just rearrange them. Now we require to calculate the value of variables, a coefficient of the variables. So here we will start with this equation. 4 minus 3 of 1 is equal to 1. So here variables are 4, 3 and 1, because we always keep the coefficient in bracket form. Now here we can see that 4 variable is there and 3 variable is there. We can replace any one of the equation, but if we go step by step, it would be easy to solve. That is, there are no chances of mistake. So here we will replace this 3 by this equation 11 minus 4 of 2. As we know, coefficient 1 does not carry, because when we multiply it by 1, the answer is, there is no change. So when 1 is there, we can ignore. So 4 minus 11 plus 4 of 2 is equal to 1. 4 of 3 minus 11 is equal to 1. Now our 4 variable value we have to substitute. So 4 becomes 26 minus 11 2 in bracket 3 minus 11 is equal to 1. So 26 into 3 is 3, minus 11, 2 into 3 is 6, minus 11 is equal to 1. 26 3 and minus 11 becomes 7 equal to 1. Now we see that with respect to 26, this x is 3, and with respect to 11, the is minus 7. So when we put this value, this is nothing but, now you can see that when ax plus by, which is equal to GCD of AB, and GCD of 26 and 1 is 1 only. The same problem we can solve in tabular fashion also. That is R1 large number, R2 we will calculate Q, we will calculate R. In the first step we initialize all this variable, that is S1, S2, T1, T2. When we calculate the Q, we will update the value of S and T. In the next step, 11 will come here, 4 will come here. The value of Q and R get updated. At the same time, we will pass this S to S, this T2 to T1 and T to T2, and updated value of S and T is again calculated based on the value of Q. The process is repeated unless our R2 becomes 0 or any one of the number is become 0. So this stop here, and whatever the value of S1 and whatever the value of T1 we collect. So the value of S1 is related with big number, that is 26, and value with the small number associated with T1, so minus 7. So in this way also we can solve for the extended Euclidean algorithm. Extended Euclidean algorithm is an extension of the original Euclidean algorithm. Computing the GCD of two numbers a and b, it also finds the coefficient x and y such that x plus by is equal to GCD of a comma b. This relationship is known as Bézout identity, and it is useful in cryptography, especially in finding the modular multiplicative inverse. For example, in RSA encryption and decryption, we require to calculate the extended Euclidean algorithm. Apart from RSA, this algorithm is used in Diffie-Hellman, elliptic curve, digital signature, Chinese remainder theorem, Hill cipher, knapsack crypto system, and error correcting codes. Now we will see some more examples. I will start with a simple example, 9126. So you will write 91. 26 into 3 plus 13 is equal to 91. So we immediately arrange this equation. Next 26 will come here, 13 will come here. So 26 is equal to 13 into plus. So we will not take this equation because one of the number is 0. Now we see that directly all this variable comes. So coefficient with respect to 91 is 1 and coefficient with respect to 26 is minus 3. And GCD of 91 and 26 is 13 because 13 is common factor which will divide both 91 and 26. Now see the GCD of 6540. So instead of explaining all the steps, you just observe this slide and you try to find out that how the equation solved. So 65, this 40, then this 40, this 25, this 25, this 15. We will not take this equation, we will write down parallel equation. So variables are, this is variable, all are variables, only bracket are nothing but for coefficient. So we will try this with the equation 15 minus 10. So here variables are 15 and 10, but we will not go for 15 directly, we will first replace with the 10. So 10 is replaced here, then we do intermediate calculation, then 15 and 25 comes. So we can replace for both, but we will start step by step. So we will first replace for 15, we will solve that intermediate step, then we will solve for the 25, and at last when we get the complete solution, at that time we can see that one is with respect to 40 and one is with respect to 65. So with respect to 65 we get minus 3 and with respect to 40 we will get 5. So you just observe the solution for this problem. Next again small problem, 98 is equal to 35 into 2 plus 28, 35 is equal to 28 plus 22, 28 into 1 plus 7. So we will arrange this, we will not take this equation, we will start from here. Now here we can substitute for the 28, when we solve we are getting this value. So with respect to 35 we are getting 3 and with respect to 98 we are getting the minus 1. And we can see that in 20, 35, 98 the greatest common factor is 7. So when we do this we are getting the GCD of A comma B. So just go through this problem also. So once you practice, it is very easy to calculate the extended Euclidean algorithm. So there is no need to explain each and every example. So you just observe the example and you will get the idea how to solve the problem. So here we have to do this step by step. So sometimes the calculation is exceed, so at that time better way is you substitute the value of variables in a step by step process, otherwise the equation becomes very complicated. And always remember that the quotient, that is nothing but coefficient, you always keep in a bracket. So this is all about the extended Euclidean algorithm. In next video I am going for modular arithmetic and Euler's and Fermat theorem. Thank you.